Hello, Christine Halsey here, and today we're going to look at how to solve for parallel circuit parameters. Parallel circuits have what's called branch currents. The supply is connected electrically to each branch. As you can see here, the power comes out, it's connected here, it's connected here, it's connected here. So whatever our supply voltage is connected across each of these resistors. That produces a certain current through each of the values of resistors. The total current in the circuit will be equal to the current through branch 1 plus the current through branch 2 plus the current through branch 3. As an example, if we have 5 milliamps, 86.5 microamps, 2.3 milliamps, and we add all of those together. Now it's important to pay attention to the units here, and if they don't all match, then we have to enter them correctly. So we have 5 milli, 5 EE3, plus 86.5 micro, which is EE negative 6. Oops, I didn't get my negative. Hang on one second. Let's go back. 5 EE negative 3. There we go, 5 milli, plus 86.5 micro is negative 6, and then we have 2.3 milli, which is negative 3. And we add all of those together and we get 7.3865 milliamps. It's milli because I can move my decimal point 1, 2, 3 places and make it 7.3 to the negative 3, which is milli. Okay, so let's try the next one. We have 50.2 milliamps, EE negative 3, plus 145 micro, which is negative 6, plus 50 micro, which is negative 6. So we end up with 50.395 milliamps. Okay. Let's look at solving for each of the branch currents given a voltage and resistor values. The current through I1, or branch 1, would be the source voltage over the value of R1, which in this case is 1 kiloohm. 10 divided by 1 kiloohm, 10 divided by 1 EE3 will give me 1, 2, 3, 10 milliamps. Okay, in branch 2, we have a 500 ohm resistor. The voltage is the same, so we have 10 volts divided by that 500 ohms. 1, 2, 3, and we have 20 milliamps. Branch 3, voltage is the same. We use R3, 10 volts divided by 25K. 10 divided by 25 EE3. And we have 1, 2, 3. That's still in front. So we go 1, 2, 3 more, and that would be 400 microamps. Okay, so then we add the 3 together. We have 10 milliamps plus 20 milliamps plus 0.4 milliamps. So 30.4 milliamps would be our total current for this circuit. To find the total resistance, we're actually using a reciprocal of the reciprocals added together. Well, the inverse of resistance is conductance. Conductance is measured in mHos, as it says in the book. We typically use Siemens, the uppercase S. So here as we look at the inverse of each of the resistors, 1 over 1K would give me 1 millisiemens. 1 over the 500 ohms gives me 2 millisiemens. 1 over the 25K gives me 0.04 milli. Now I left it this way for addition purposes so they all match and it makes my math easier. I can say 1 plus 2 plus 0.04 for 3.04 milli. Then I take 1 over that final answer for 329. Now let's look at doing that on the calculator. Okay, there's a couple of ways you can do it. I prefer, let me clear this out, if you do it one step at a time, like I've written out here, and do the 1K, 1E3, then I can say 1 over X, and that gives me that value. I can store that in memory. Alright, then I can take 500, 1 over X, and then I can add that to what's in memory. I don't think it did that right. Let me try that again. So I've got my 1K, 1 over that. I'm going to store that in memory. I think I'll just use a recall. Alright, so then I've got 500 and 1 over that. And I'm going to add that to what's in memory, get my answer, and store it again. Then I can take my 25K, 1 over that. Oops, I didn't do that right, did I? 25 EE3, 1 over that, plus what's in memory. Alright, so that gives me my final answer here, and then I need to invert that one more time. And that gives me my final answer, 328.947 ohms. Now, always double check your work with parallel resistors, and the best way to do that is to always make sure that your answer comes out smaller than the smallest resistor. So in this case, our smallest resistor was 500 ohms, and our answer was 329, so we're in the right range. Let's look at solving for a branch current that has a potentiometer in it, and we want to use it to set the total current in the circuit to a value. So the first thing we want to do is solve for the current that we can already find, which is I1 and I2. So we have 10 divided by 1K. So 10 divided by 1K gives us 10 milliamps. Let's try this, 10 milliamps. Okay, then our next one is 10 divided by 500, which is 20 milliamps. Okay, so let's say we only wanted the total of current in the circuit to be 35 milliamps. So we'd have 35 milli minus the 30 milli of the combination of I1 and I2, and that would leave us with 5 milliamps for the remaining branch. Well, R equals V over I, so now I can take the 10 volts divided by my 5 milli. Yeah, it's not easy writing with your finger. And when I have 10 divided by 5 EE negative 3, that tells me I'm going to need a 2 kilo ohm resistor. Or I need to set my pot to 2 kilo ohms. So let's look here at how a current source would divide on the branches for each. So we have our total resistance that we would have to find first. Same way we found it last time, the reciprocal of the reciprocals added together. So we have 1 over 1K. The only difference here is the 100 kilo ohm. That became 0.01 millisiemens, which changed it to 3.01 millisiemens here, which gave me 332 ohms. Once we know the total resistance, then we can take that total resistance and begin to solve for each branch current. Now the current divider rule works a little different than the voltage divider rule. Instead of putting the resistor you're solving for on top, we actually put it on the bottom and the total resistance goes on top. So I have my source current, 900 microamps. EE negative 6. And that's 900 micro. Alright, I'm going to store that. Times 332, which is my total, divided by 1K. And I come out with 298, 299. Let's make that. And then this is milliamps. So is this, and so is this. We'll come back and look at those. I just had to fix that. Okay, so my 900 microamps times 332 divided by 500. 123, 598 milliamps. And again, 900 micro times 332 divided by 100K. 2.99 milliamps. So then I add all those together. And due to rounding, I've missed 3, not quite a whole 3 nano amps. So if you don't round these, it should come out pretty perfect. If we took all 3 of these numbers exactly and added them together, well, this one, let's see if I can do that, plus that, plus that, and I got something wrong. I thought that was working, but it didn't quite work. Let me try it again. This. There it goes. Alright, anyway, you can add them all together if you add these specific values that we calculated, then that's exactly what it should come up equal to. And next example here, we're going to look at the power for each of those branches. You can use I squared R, you can use I times V, so we could pull in the currents we calculated here and find the voltage drop. And it's easier here, we know the voltage in this case, so we use V squared over R. So 10 squared over 1K. Okay, so 10 squared is 100, but I can plug it in. 10 squared divided by the 1K gives me 100 milliwatts. 100 divided by R2, which is 500, gives me 200 milliwatts. And then divided by 25K would give me 4 milliwatts. So we have a total of 4, 100 and 200, so 304 milliwatts. If you know the total resistance, you can check that by 10 squared over the total resistance. In this case, 329 ohms. $304, 1, 2, 3, 304 would round up milliwatts. There we go. And this example is kind of like solving a puzzle. So to find the value we need to find, which is I3, and from I3 we can find R3. Alright, so here Vs is actually going to be equal to the same voltage here and here and here. So if we know the current through this branch and we know the resistance of that branch, we can solve for the voltage. So our voltage is 3 volts. We can then take and solve for our total current because we have the total power. Total power divided by voltage will give us the total current. Alright, which in this case is 0.43, so 430 milliamps. Okay, 430 milliamps. And then to find I3, we would take the total minus I1 and I2. I1 is 300 milliamps. We have to solve for I2. Okay, so we solve for I2 with V over R2, 3 over 30 ohms, 3 volts, 30 ohms gives us 100 milliamps. So then I can take my total current and subtract out I1 and I2, or I1 plus I2, and we get a total of 30 milliamps left for R3. Okay, so using V over I, we solve for R3, 3 volts, 30 milliamps, and I think you'll find that gives you somewhere 3.3 times the size of R2. So the greater the value, the resistor, the lower the value of the current. And our last one here, again, is pretty much like solving a puzzle. They want to know what IS is. So first we solve for what we can. We know I3 and P3, so we can solve for R3 using R equals P over I squared. That's a derivation of P equals I squared times R. And we divide through by I squared to get R3 by, or R by itself. We come up with 150 ohms. So now we know P equals I times V. We can use that and solve for V. So V at P3 would be that power divided by the current. And that would give us the voltage. To solve for the total current, we would then put those three values of a resistor, 100, 300, and 150, in parallel using the reciprocal formula 1 over R1 plus 1 over R2 plus 1 over R3. And once we have that total resistance, we can then turn around and use the voltage that we solved for here and divide that by that total resistance to find the source current. Thank you and have a great day.